I don't know how much you remember about word problems from grade 10. You do a little bit of them in grade 11, but then not much after that. Some of this process is going to be very similar. Some of the questions are very similar to the ones you did in grade 10. In fact, the first one we look at, I think, probably could be solved. I don't see why not with grade 10 techniques. But you're not allowed to do that. We are only using calculus to solve these. Some of them could be solved with grade 10 techniques, but a lot of them can't. But otherwise, even regardless of whether it's one type or the other, some of the process is very similar. Okay, so the questions are a little bit more complex, generally speaking, but a lot of the steps are going to be similar. The steps that are outlined here, and you have these same steps on your page, are just guidelines if you like that sort of thing. They are good if you're stuck. There's the step number 1, 2, and 3 can help get you started, can help put your focus in the right track. So I would kind of remember that those are 3 good techniques to start with. And then the other stuff is just little reminders of what we ultimately have to do. But like I'm not looking at this personally as a step-by-step process. That being said, there are some nice tips in there while you're working on this, or if you ever get stuck or that kind of thing. And some people just like to have a step-by-step process or algorithm to do this stuff, right? So you can read over those on your own if you want. We will be doing basically those steps. The exact order in which you do them, again, doesn't necessarily matter. That may change depending on the question or depending on the person. We have different preferences. We're going to cover all 6 of these, 3 today, 3 on Monday when we come back. So questions 4, 5, and 6 are our note for Monday when we get back. And 5 and 6 are very different kinds of questions. They would probably be hard to figure out on your own. And you might sort of think about these as different, like identify the type of question when you're working on them. If you're following the guidelines, then they'll get you going no matter what kind of a question it is. But there are different types. So if you do the practice and you've done a couple of each type, that'll set you off on the right foot where you're like, oh, this is this type. I know that it's going to have this trick in it or something like that. Does that make sense? Any questions? So let's take a look at the first one. It's about fencing. A farmer has 1,600. It's always interesting to sort of reflect on what information you're given as well, right? A farmer has 1,600 meters of fencing with which to create 3 identical regular fields. So it's not just one big field, it's 3. But again, that was probably something you did in grade 10. If one side of each field needs no fencing because it's against a river, find the dimensions of the field that will maximize the area. So area, which I'm going to call A, is to be maximized. Again, whether you start with this statement or whether you start with the diagram, it's entirely up to you. Now I'm going to draw a river. And I'm going to draw my field up against it. But it says 3 identical rectangular fields, so I'm going to take that and split it into hopefully 3 moderately similar looking rectangles. Does that make sense? A big part of these questions is the diagram because it's going to really help with a couple of steps. One we're going to do now, but one we're going to do in a little bit. And like without the diagram, it would be a lot trickier to visualize this stuff, right? Because it's not always going to be 3 identical rectangular fields. It's going to be other ones. And again, the visualization just really helps. So I've got a width, which is that whole thing. And I've got a length, which is this whole thing. There's a couple of ways you could approach this type of question. I'm going to do it one of the ways. You could try the other and decide which one's your favorite. They're not that different. And I'll tell you sort of how they're different. The algebra works out a little bit differently, but I don't know that one's really easier or harder than the other. I'm going to call the width x. And I'm actually going to go with y's for each individual length of the fields. But you could do the problem with one big L or one big Y. It would work. Like I say, it's slightly different in the way the algebra works out. Okay, so let X represent the width. And let Y represent the length of one of the small fields. If you remember, these let statements, some people take them for granted, but they have to be specific. If you say things like, let X represent the field, which I don't think you would say in this case, but there are some other kinds of questions where people say that. Like, what do you mean the field? What about the field? You've got to be representing some measurement or something that's a number. A field isn't a number, right? So you got to be specific. So again, the diagram will help with what Y represents. So if you have a diagram and you have the Y labeled there, it may not be as important, but you want to be careful that you're specific about what these things represent. Make sense? So now I can do area. So area is the thing that I'm maximizing, A. So I gotta find the formula for area. Like I gotta come up with an equation for area. That's the whole point. What is the equation for area of a rectangle? Length times width. What is the length? Very good, it's 3y. And the width is x. So this is 3y times x. But if we go back to our little tips up above, we have to write a formula for what is to be maximized or minimized, which in this case is area, so that's where we've started, but it's got to be in terms of just one variable. And we don't have that yet. I mean, I have 3 variables, but the a doesn't count. Okay, the a is allowed to be a second variable. It's here where I've got x and y. That's trouble. So what do? And often these questions have this little side step where we go off to the side and we do some other work so that we can write y in terms of x or x in terms of y, and it's probably going to use the value that you're given, right? And if you have a heads up on the different kinds of questions, then you might have a heads up on exactly what this looks like. Because for all the field questions, it's going to kind of be the same. Does that make sense? Otherwise, you're going to have to actually think and figure it out, which is harder. So in this case, I've got 4 x's because I've got x is this width, but I've got all 4 of these widths or lengths of fencing to split up this pen, right? All those black lines are fences. So all those black lines have to add up to the 1,600 meters of fencing total that you've been allowed to use, that you have available to you. So I've got 4 x's and 3 y's that have to add up to 1,600. And in this case, you could either solve it for x or solve it for y. I think it's going to be, I'm going to solve it for y. I think it's going to be easier. You don't want 3y, you want y. And this is where, so at this point I have a fraction. But it turns out it's not really going to be a problem because I'm going to take this y and sub it back into my equation and write this 3y, which is 1,600 minus 4x over 3 times x. And now that I have a function written in terms of a single variable, I'm actually going to use function notation just because it's going to be kind of nice for later. And call it a at x. Any questions about that so far? That's like all, or almost all the pre-work that we need before we start doing like the procedural math part. That's the setup, right? The nice thing here that we notice is the 3's cancel. And I'm going to expand this through, so I get 1600x minus 4x squared. So as I said, this one turns out to be quadratic. There's a small check here that you can think about for some kinds of functions if it's quadratic. We're supposed to be maximizing the area. This is a quadratic that opens downwards because the leading coefficient is negative, so it's going to have a maximum. So that's a good start that I've got this far. Fits. Doesn't mean what I've done is exactly correct, but if that was positive, I would know it was wrong. Okay. What do we do now? And again, this is where all of those skills from the last unit of taking derivatives counts, because if you left it in this form and used the product rule, and it's just a bit more complicated, right? Like, why wouldn't you expand to get it a polynomial? But how do you know when to do that and when to do the other? It's an art. So what do we do next once we get this expression or function that we're happy with? We take the derivative. Because where do maximums and minimums occur? They occur where the derivative is equal to 0, and also where the derivative does not exist. Simple derivative. This derivative exists everywhere. So I need to think about that whenever I'm doing a question. But I don't need to do anything about it in this case. So we're just going to set it equal to 0. I'm just going to make a note as a reminder. Max or min occurs when derivative equals 0 or does not exist. But like I said, there aren't any places this is a polynomial where it doesn't exist, so we don't need to worry about that. That being said, there will be some questions where we have where a derivative does not exist. I'll give you a little hint. It's rare that that's actually going to be the answer. But if you have an expression that has a place where it doesn't exist, you need to take it into account. Like and we'll see that come up in the next example, I think. But like, it's not usually the answer, because that would have to be a cusp, and these rarely have cusps. There's just, I don't know an application that works out that way. Okay, so there's a hint, but 1600 minus 8x equals 0. Oh, I'm going to go back and I'm going to go, so a prime at x equals 0. This is where max or min occurs. So x is 200. I can't remember what the steps say, but it's there's 2 more steps. One, we have to answer the actual question. Maybe x is all we needed, but maybe we need both dimensions, or maybe we need the total area or something like that. Like, I don't know. We're going to talk about that again in a minute. We have to go back and answer it. And the other thing that we've included is this little check. There's a couple of reasons why you want to do a check. I mean, I know a lot of you like when there's some way of checking your answer. So that's part of this process. But also, and again, this one's quadratic, so it wouldn't happen in this one. But there are cases, I'm gonna draw and then erase it, so don't copy this down. There are cases where you have a horizontal tangent line where the slope is equal to 0, but it is not a max or min, right? So if this was my function and I found this horizontal tangent line, how could I determine whether or not it was a max or a min? Again, this actually won't usually happen, but it technically could. So we're including the check just in case. So our check is going to look like this. I'm going to check a number just below. I'm going to check the value there. And I'm going to check a number just below or just to the left. Check the value, check just to the right. And compare those three values. And I'll know which one. I'll know that it's a local max or min versus just something like this. Does that make sense? If I did just to the left and my actual value, which in this case is 200, and just to the right, one would be below and one would be above. And I'd be like, oh, this is not a max or min. Okay, so we're going to do this check for those two reasons. So I'm going to check A, and you check back in the original function, not the derivative. That would be useless, right? We're checking back in the original function. I'm going to check just to the left. I'm going to check the point we came up with, and just to the right. How far to the left and right exactly you have to go? There's no rule on that. Reasonably speaking, reasonably close. And when I sub these in for the 200, I get 160,000 meters squared. And for the other two, I happen to get the same one because I went the exact same distance, and they're quadratic, and that's how quadratics work. Usually that won't happen. Often that won't happen. So now it's a little bit more obvious why we do this check and why it works. We were trying to maximize the area, and that point does look like it clearly the function turned between those two values. Somewhere between 190 and 210, it went up and went back down. This is not a proof that that's the exact value necessarily, but it would be strange that you happen to get a value in that interval. So, I mean, it's a pretty good check. You know what I mean? But if this was smaller, and then you had this one, and then this one was bigger, you've made a mistake, or you've got a horizontal tangent line and the function is continuing upwards, not turning back down. Any questions? So that's what our check looks like. We usually give it a little title. Check. And this next part's a little bit weird because this question in particular is a little bit unspecific in what it's asking us to find. It says find the dimensions of the field. Does it mean the whole big field or each little field? So I'm going to answer both questions. If the question on a quiz or a test is specific, make sure you answer the question because we're just looking that you're taking the care and thinking about this stuff. Okay, and it is going to be something where you always are going to have to think about, well, I've got multiple dimensions here. I've got W and X, they're actually the same, but I've got Y and I've got L. So like, what am I looking at here? What have I actually calculated? Okay, so we got to think about that. So I'm going to come over here and do some of these calculations and then make a final statement. So when X equals 200, there's my formula. Y equals 1600 minus 4 times 200 over 3, which works out to 800 over 3. And that's one of the small fields. This is not my final statement, but so my width is 200 and my length is 800. 3 of those, right? Therefore, the dimensions of the entire field are 200 meters by 800 meters, and each individual field, is 200 meters by 800 over 3 meters. Sometimes the question will be specific. This one seemed awkward. Find the dimensions of the field. what field. Any questions on that one? Kind of familiar, right? You've seen this kind of stuff before. Like I said, some of this is very familiar. Some of that prep stuff at the top looks a lot like what you would have done in grade 10, if you can remember back that far. All right, question number 2. A manufacturer wishes to produce a cylindrical fruit juice can with a capacity of 250 milliliters. What dimensions will minimize the amount of material required for a can? No conversions are required. You probably wouldn't even really think about it, but dimensions of a can will be in centimeters or some length, whereas capacity or volume would be in like liters or milliliters, right? But the conversion, that's the great thing about metric is direct. So 1 milliliter is 1 centimeter cubed. So we don't have to worry about any conversions, and rarely you would, maybe something simple like centimeters to meters, right? But not in this kind of a case. And this makes sense that a company would do this. So no matter once we finish this, we'll talk about this again, but no matter what dimensions we use, we're going to come up with an equation that will always have 250 milliliters as the volume. If you're a company and you're making a drink and you want it to be that volume, but you want to minimize the cost of your material, what size of can would use the least material? Minimize your costs, maximize your profits. Why wouldn't you do this? Right? So it makes sense that a company would want to do this. And again, one of the first things we might want to do, you might start with your diagram, you might start with this, but we're minimizing the material required. What is that? That's surface area, isn't it? So surface area is to be minimized. We kind of do this in grade 10, but not quite as formally, but I really think it's important. I think it's really helpful because our questions start to get a little bit more complex, that it helps you focus. So now I need to come up with an equation for surface area. Like that's what I need to do. And I take the derivative of that, and that will find me the maximum or minimum, whatever I'm finding. All right, I'm going to draw this thing out. So I'm going to draw a cylinder. What are the dimensions relevant to a cylinder? Radius and height. Now I can define my variables. And I create a formula for surface area because that's what I'm trying to maximize or minimize in this case, but whether it's maximize or minimize, right? That's what you need to be coming up with a formula for. If you did this question and you started with volume here, and you wrote an equation for volume, like you're done. That's it. Question's over. You might get 1 or 2 marks for the diagram and the let statements, but that's it. It's just going to be nonsensical, everything that happens after that. So it's really important that you think about what you're maximizing or minimizing, and that's what you're writing the equation for. Because sometimes that happens. People get so confused. It's a surface area question, and they start working on volume. Anybody know the surface area for the formula for a surface area of a cylinder? I didn't think so. So it's 2 pi RH plus 2 pi r squared. 2 pi r squared is the circle on the top and on the bottom. If this question didn't require a top, that's something that might happen. You would have to modify the formula. It would be 2 pi rh plus pi r squared, not 2 pi r squared, right? Because I've got two circles, one on the top and one on the bottom. That's the 2 pi r squared. And then the long part is the 2 pi rh. Why? Because 2 pi r is circumference of the circle, and it's a rectangle when you unroll it, and it's 2 pi r times h. That's how a cylinder works. You don't need to know that, but it can be helpful to if you ever need to think it through. Okay, so now the problem is this might be a nice way of doing these questions. I've done as much, but some people may choose to do it in a different order. I've done as much work as I can here. Now I have an equation that's in terms of two variables. Pi is not a variable, pi is a number, so that's not one of them. I've got an r and an h. So I got to do something about that. And I think I mentioned this before. Usually it has something to do with the value that we're given. The value we're given in this case is volume. But we're given the volume. We're not maximizing or minimizing volume. We're given the volume. So now I use that to rewrite one of the variables in terms of the other so I can sub back in. So volume. Does anybody know the equation for volume of a cylinder?
Is it 2 pi r squared h?
Close. It's 1 pi r squared h. Good. Pi r squared is the, again, area of the cylinder on the bottom, and then you multiply through by the height to get the whole volume, right? And volume is 250. But this is what I mean. If I started with volume over here, like you could start with the volume. I mean, you could start with this step if you want. If you know you need to rearrange this equation, you could start with that. That's not my point. My point is if you're taking the derivative of a volume formula for a surface area question, you're done. Okay? So 250 equals pi r squared h. You could do either. If I rearranged for r, I'd have a square root function. I don't want to do that, so I'm going to rearrange for h. And now I can sub that back in. You don't need these arrows, but it kind of reminds us that like I'm doing all this work over here, sidestep, do this, and then resume. And just replacing h with an expression in terms of r. Now that I've got a single variable, you don't have to do it in this step. You can do it in the next step if you want. I can use function notation. I can do a little bit of simplifying here because I've got a pi on top and a pi on the bottom. And I've got an r here and r squared here, so I'm getting rid of just one of the r's. So surface area in terms of radius is 2 times 250, which is 500 over r plus 2 pi r squared. What do we do when we have an equation we're happy with? Take the derivative. Okay? If you still like the idea of rewriting 500 over r, I'm going to do this off to the side, but you know, you might be getting to the point where you don't have to do this. It would be 500 to the r to the minus 1. I don't know that you really have to rewrite that. If it was some other exponent, maybe, or if it's like a rational exponent, like a negative 1/2, sure, maybe. But I know it's negative 1. So I just know it's going to make the whole thing negative. And then I'm going to subtract 1, which is going to be r to the negative 2. So it's going to end up being over r squared. So I think I mentioned this the other day. Like, this is the kind of thing that once you've done it a bunch of times, you kind of know how it's going to work out, and you don't need to rewrite and do all that fancy stuff. You can probably just get there. So negative 500 over r squared plus 4 pi r. Is that okay? What do we do now? Say again? Good question. I should have mentioned this. Pi is not a variable. So I'm not, it's just part of the constant. So it's not in this case. You won't have any implicit stuff with this. You won't have different variables. Remember, our equation has to be in terms of one variable. Otherwise, we're doing implicit derivatives. And that's not going to come up in these word problems. So there's another tip. There's no implicit stuff. So don't get yourself confused there. It could be product rule if you had 2 big brackets. Like the one question had that, but we simplified instead of doing product rule. So usually you're going to be able to avoid product rule, but not necessarily always. What do you think we do now? Yeah, and how are we going to do that? We're going to have to fully simplify, right? So in this, which means one fraction. So I've got to multiply this one by r squared over r squared. You could do that later. You could do it now. I like to get this part done for these kinds of questions here before I start any of the next step. So I'm going to get, and I'm going to rearrange this a little bit. It ends up being 4 pi r cubed minus 500 over r squared. So I just multiplied the second term here by r squared over r squared to get a common denominator. Fully simplified means fully factored. I don't need factoring the 4 out, that's not really going to help us. So you could do that or not. We're going to eventually sort of do it anyway, but it doesn't need to be done here. That part's up to you. If it was factorable in any other way, on top or on bottom or whatever, you might do that. Okay, but so tell me something about this. What do you think? Right, it has a place where it does not exist, so that's interesting. But if we look back, so did our original function. If I had simplified this one fully, I would have it over r as well, right? So that it's a vertical asymptote, so it doesn't matter. But we're just going to do this. Surface area prime at r does not exist at what's the value that it doesn't exist at? Anybody? Yeah, 0. So somebody tell me something about that. Would this be a good value for the company to use to make their can? No. A can with a radius of 0? No, I don't think so. So, like, it doesn't make any sense. So you could think about it that way in this case and say that it's inadmissible because it's senseless. Okay, so now we're going to figure out where the derivative is equal to 0. So that's when the top is 0. I'm going to move the 500 over and divide by 4 pi. Take the cube root of both sides. And 500 divided by 4 is 125 over pi. which is about 3.41. 3.4139. 3.41. Any questions about that? Couple things left to do here. One of them is our check. So it's useful to have the decimal value so I can come up with numbers that are just above and below. I'm finding the actual surface area. We're minimizing surface area. So when you do the check, you're finding the actual surface area that would be the minimum. So you sub back into the original equation. If you subbed into the derivative here, that would be useless. Sub into the original equation. So I'm going to use 3. The 3.41, but it's not so bad, so I'm going to use it as an exact value. I can punch that in my calculator. And 4. And you get 223.2, 220, these are all rounded, 222.82, and 225.5. So again, it looks like it's a minimum. Looks like it's fine. It came down, hit a minimum, and went back up. Okay, and then we're just going to, it says find the dimensions. So when r equals the cube root of 125 over pi, h equals 250 over pi times the cube root of that thing squared, I think is a formula, which is about 6.9. Those are rounded. I think the way it always works is the radius would be exactly half the height, or the height would be equal to the diameter. That's what would maximize volume or minimize surface area, which is funny. So like tuna cans that are totally out of whack, or tall, thin cans, waste of material. Some companies obviously don't care. Any questions about that? That's all in centimeters. We got one more to do here. And so this one is about dimensions as well. The first one was about area and perimeter, and it was a field question. Second one was about a cylinder, and we were minimizing surface area. So this one does have a twist to it. It's a little bit different. A box with an open top is to be made from a square piece of cardboard. So we need to come up with a square with side lengths of 100 square, so 100 on each side, and cutting a square out of every corner. What in the world is that talking about? And the fact that it's an open top box, by the way, is important. What in the world is it talking about? Yeah, very good. What a strange coincidence. I happen to have an example of one right here. So I took, this is a rectangle, but you get the idea. I cut the corners out, roughly similar size, so then when I fold all the flaps, they have to be the same length, so that has to be a square, so that those meet properly, right, and flush. If you can't see that at the back, you can come up and take a closer look later, right? But once you kind of see it, you're like, okay, yeah, I see what's going on here. And all the corners have to be all the same length of cuts, so that all the sides are square and flush. And this is sort of a box. So what does that mean? That means we're starting with the square. Find the dimensions of the box of largest volume. So volume V is being maximized. I'm going to draw this out twice. You don't have to do both diagrams every time, but well, that was interesting. The second diagram will help us figure out where the dimensions go a little bit. I don't even know where that came from. Down here. Am I going to fall entirely? Okay. I'll be careful. Try not to roll around. Okay. So we're going to cut out. We're going to start labeling this a little bit. First of all, it's 100 centimeters. (100 centimeters) all the way across. And I'm cutting out squares. Again, this is another one where if you have some advanced idea of, first of all, what it's even describing, what it's talking about, and how this diagram looks and where your dimensions get labeled, it's going to really help. If you were figuring this out from scratch, I think you would struggle. I think it would be very difficult. It would be a challenge. So you want to kind of have a heads up of what's happening here. Where do you think we're going to label things? Where are we going to put our variables? Anybody have any ideas? What are the things that might change?
Well, you could label each little side length with a small box like X.
Yeah, very good. So that's what we're going to do, because that's what's going to determine the dimensions of the box. If I cut bigger squares, the flaps would be longer, right? So the length and the width would be shorter, but the height would be bigger. So that's what's going to kind of change things. And depending on how, so I don't have to label all of them every time, but every single one is going to be X, right? And depending on how big that X is, will change this. And that's where we put the other variable. So I'm actually just going to define, I do have a Y here, which is going to help me visualize this stuff, but I'm just going to define one variable in this case, because the Y would be hard to describe. Yes?
Could you also put Y, instead of Y, put 100 subtract 2X?
Right, which is what we're going to do anyway. So thank you. So that ends up being 100 minus 2x. You didn't even let me ask the question. On every side, right? Let x represent the length of the cut corners. Okay, bear with me while I try to do the second kind of diagram. It's a trickier one. I am going to start with a diamond. Oh, that didn't work. Try again. There we go, nice. Okay, start with a diamond, and then I'm gonna take my, from each corner, I'm gonna try to come down sort of exactly the same amount. And I'm gonna connect those corners with hopefully a line that's kind of parallel to the one above it, right? That's gonna help it look proper. And do the same thing here. Like that. And it kind of looks like a box. Does anybody know, this is one you might know, the formula for volume. So what we are maximizing in this case is volume. So we need to come up with an equation for volume in terms of a single variable. What's the equation for volume of a?
Squared x.
It would be, but what is it just without x's and y's? What's the actual volume? Yeah, or we'll say length times width times height, base times width, whatever you use. Yes, very good. And it would be, but two of them are y's, so y times x. But my y, which is going to be here, is actually 100 minus 2x and 100 minus 2x, and the height is going to be x. So this diagram can help us visualize what the dimensions are. But ultimately, we need to recognize that it's 100 minus 2x times 100 minus 2x, or 100 minus 2x squared, times x. So this looks like a messy product rule, but I think it's going to be way easier to just expand. So negative 2x times negative 2x is 4x squared. I'm going to multiply through by x as well, so I actually get 4x cubed. I get negative 200x minus 200x is negative 400x, times the other x is minus 400x squared. And 100 times 100 is 10,000, so plus 10,000x. What's next? Take the derivative. Exists everywhere, so we don't have to worry about that. You do need to think about it, but you don't have to. But in this case, we don't have to do anything about it. So when v prime equals 0, and we can divide through by 4, it'll just make things a little bit easier. Now that it's equal to 0, it's easy to divide by 4. I don't even have to factor it out. Like I am factoring it, but I'm just dividing it out, right? Divide it on the other side by 0 and it's gone. B squared minus 4ac for this is 100. Or actually, sorry, it's 10,000, which has a square root of 100. So this is factorable. So you could try to factor it if you want, but I'm just going to use the quadratic formula because I think factoring it would be tricky. And that works out, like I said, to 200 plus or minus 100 over 6. What do you think? Yeah, you should always show the substitution. But then you can go, you don't have to show any extra steps. You can go as far down to the answer after that as you want. What do you think? What do you think about those answers? Do you like them? Do you not like them? In grade 10, when you start doing these and you get 2 solutions, this is where you start getting 2 solutions in grade 10. And you circle the negative one, you say it's inadmissible because the first ones you do typically involve time. And then on the test, like 10% of students, for every question on the test, even if it's just solve the following, it has nothing to do with the real world, they circle the negative one and they say inadmissible. It's like, oh, apparently all negative answers to everything are inadmissible. I've even seen some students throughout other units of the course saying negative things are inadmissible. It's like, no, no, no. Sometimes answers are inadmissible for a reason. Yes, you don't have negative time. You don't have negative length. Doesn't make any sense. Neither of those are negative. So what do we have? Two answers here? What do we have?
We have to go back and test.
So what do you think about those? We're running out of time here, so I want to do this so I can hand back your tests. But if I sub 50 into there, what do I get? 0. That's not a maximum volume. What is that? That would be a minimum volume. Which makes sense. This is cubic, so it's going to come down and then go up, right? It's going to have a max and a min. That would make sense. So that, but that one, you don't have to really know that or worry about that. This one is inadmissible. Very quickly, I'm just going to write out the check. So I've already got the values. So we're at about 16, so I'm going to do 15 and 18, just because that's the one I have written down here. 73. So the maximum, so we're good. That means when x is 50 over 3, y is 100 minus 2 times 50 over 3, which is 200 over 3, which is about 66.7. Therefore, the dimensions of the box should be blah, blah, blah.